we talked about compression members last time, and compression members means that a member, whenever you see member or members here, that means a structure, right? So this is a structure. What kind of structure we are talking about? Column. We're focusing on the columns. So here is the long columns with central loading. So this is buckling. So buckling, we have four key scenarios. So first one is the two. This is the two ends, and they are pinned. And they are pinned means that, and the translation is fixed. For this one cannot translate in this direction, either in this direction either. But it can rotate, right? So the rotate is allowed. The horizontal here is rotation is allowed. And the second one is this one is fixed. Fixed means that cannot translate, cannot rotate. Here is also a fixed. The third one is this end is fixed, but this end is free. Right? Is free. After you apply load, it will go here. It will go different. The last one is this one fixed, and that one is pinned. So we totally have this is the four case scenarios. Four case scenarios is a C. And C critical load. Okay, so this is a critical load. So what is the meaning of the C? The C is a factor that corresponds to this is the case scenarios. So for us to calculate the critical load, what is the critical loading condition? You can see for the pin-ended column for this one, the critical load is given by this Euler column formula. Euler column formula. This Euler is a person's name. And so how to calculate this guy's critical load? Critical load means that at this point, the structure loses the stability. Right? So this is a critical load. This critical load can be calculated using this equation. Young's modulus I is a cross-sectional area, which is the geometric parameter I, and IL is the length of this material, of this structure. And pi, we know pi is the constant. E is Young's modulus. You can see on this equation, PCR is influenced by the material and by the geometry, and also by the length. And the geometry here, I talk about the cross-sectional geometry. So applies to other end conditions with additional of constant C for each end condition. So this one is the basic one. So this first one is the basic one. For other three cases and some other mathematicians, they just give us these results. We want to accommodate all these four case scenarios by using one equation, right? So you can see PCR equals this one. So I square EI L square, that is a PCR for the first one. So that's the reason we see C equals 1. So this is our first case. And for other three cases, it is dependent upon the ending conditions. And then to select the C. So as I said, PCR is a critical load at which the structure loses stability. You understand? Okay, so we can, if we have these equations, or if we have these case scenarios, and we can use this equation to calculate the PCR. These are here recommended values are for end condition constant. This is a four conditions here, and fixed conditions are practically difficult to achieve. Fixed condition are difficult to achieve. So more conservative values of C are often used in this table. So here, the four case scenarios fixed, one end is fixed, another end is free. So for this case, rounded, and so this is a pinned here. Fixed, rounded, and fixed. These are theoretical values, and these are theoretical values. So sometimes we use conservative values. And so this is our recommended values. be conservative, we use these values. Even though this is theoretical value. Theoretical value, when we apply this law in the context, in some context, because other unpredictable this is vectors, the results, the stability can be influenced substantially. Okay, that's the reason people propose to use conservative value, which is much safer. I'm a conservative guy, and whenever I design something, I prefer to use more material, a bigger structure to make sure it will not collapse. How about you guys? Want to take any risk? Okay, good. So this is one is a concept here. I equals, and I is every moment inertia, and you for this is a beam, okay, for this long beam, and we introduced this is the radius of gyration. So be very careful. We have this is a k, and k here is the radius of gyration. Okay, so this is new thing. Whenever we learn new things, we pay more attention to this one. And how this is okay? I equals a and k squared. Right? So I is area moment inertia, and a is a cross-sectional area. But we can use use this equation to calculate the k. So k equals square root and I over a. So the Euler column formula can be expressed, and we just plug in this I, and we plug in I here. So this is the can be calculated PCR. Okay, so this is a PCR, the critical loading, and divided by A. A is your cross-sectional area. It equals C and pi squared Young's modulus. So L over K and square. Now, we have another concept. So this is our first concept. I will put a question, put sum up here because it's a new to me, to the students. If you have never seen this guy, and then second, the term is L over K. Okay, L over K, and so this guy is termed the slenderness ratio. Slenderness ratio. How slender this guy is. It takes care of the length and also A, T. This is A, this is K, I'm sorry. K is associated with area. Slenderness, length, both the length, also the cross-sectional area. What? So this is understandable, right? You can imagine. I'll say I have a very long beam, but the radius is very huge. But still, the buckling is not likely to happen, right? Do you agree? However, if the length is relatively small, but the cross-sectional area is very small, and still it is very highly possible that it will be buckling. You guys agree? That's the reason we introduced this is the second. The concept, slenderness ratio. How thick can this guy be? How thin this guy is? Not how thick, how thin this guy is. So PCR over A is a critical unit load, okay? Unit load. Why? I divide this PCR using the cross-sectional area. So critical unit load, the load per unit area necessary to place the column in a condition of unstable equilibrium. So this is called the unit, a critical unit load. Because I divide the PCR and using the cross-sectional area. Questions regarding this slide? Okay. Slenderness ratio, critical unit load. Questions? Question? So we plot this curve on PCR over A versus L K, L over K. L over K is the slenderness ratio, and so for this case is a C equals 1. So this is this is the curve. Okay, so this is the curve. So this curve is Euler curve. This is Euler curve, and so this is a parabolic curve. So this is Euler curve, and this is a parabolic curve. Euler curve, okay? So Euler curve, if your slenderness ratio is greater than 1, greater than this value, and we use the Euler curve. Otherwise, and we will use parabolic curve instead of here. But as I said, so this is L over K is a very, very important one, important value. And so how to calculate this one, L over K, how to calculate this value, and this is first step. So this is the test show vulnerability to failure near the point Q. This is vulnerability. So since buckling is standard and catastrophic, a conservative approach near Q is needed. So point T, okay? So we find this is point T. And point T is usually defined such that PCRA is a critical unit load, is half of this is the yield strength, and we will use this equation to calculate this critical slenderness ratio. Yeah, I posted these slides online already before the class, usually on the weekend. So if you are using computer or this is other smart these devices, you can just pull it out and draw down these important things. Okay. So here, so as I said, so this Euler curve, but here the rationale here is saying that because here is very, very catastrophic this phenomena for the catastrophic nature of this is the buckling. So we will be some kind of conservative, and we will use this dotted curve instead of this one. Okay? Now, and how to calculate and how to be conservative, and we are going to use this dotted curve to the left of the T, and use this Euler curve to the right of the point T. However, and here is the critical slenderness ratio, L over K. So this guy is calculated using this equation. So our assumption is the T is half of the yield strength of your material. So P using this one, and we can calculate L over K, and so this is the equation how we calculate the critical is L over K, and we call this 1. So this one equals 2 pi square CE over SY. 1/2. So calculate this one first. This is the critical slenderness ratio of the beam. Questions so far?
And SY is the yield stress.
Yeah, SY is the yield strength of the material. That is material parameter. Good question. SY is the yield strength of the material. In this figure shows that the maximum one is SY because at that point, is the material yield. Material start yielding. Questions so far? Question? No question. Let's move on to the next slide. If LK, so if so this way is a critical value, okay? So this is a critical value. If your actual slenderness ratio L over K is greater than this guy, and we use this Euler curve. However, if your actual standard distribution LK is smaller than this critical value, and we use parabolic curve instead of so this one, right? Because this one is kind of risky. This is too aggressive. It's risky. Questions so far? Now, how to calculate this LOK? And we use this equation. The Young's modulus, use the strength of your material, and also the case, what C is. For intermediate length column with central loading. So for intermediate length column, usually, so this is actual standard distribution is smaller, okay? Is smaller than the critical L over K, and then we use the parabolic curve. We use a parabolic curve here, between SY and T. So general formula of parabolic. So this is the equation, right? Equation. So if parabolic start at Y, and you can, just if we start at SY here, so when L over K equals 0, I have Y. When this one equals 0, so this one is SY. So A equals SY, right? It's understandable, right, guys? And then if the parabola is tangent to your Euler, if this guy and this one is tangential to each other, and so you can calculate this B, this B value. So as a result, the parabolic formula is given here. Parabolic value formula is given here. So that's using this one, then we can just describe this behavior of material for all this is L over K. Either our L over K is greater than this critical one, or our actual L over K is less than this critical value. And we will use different equation. So here we some also called is a Johnson formula. It's a Johnson formula, and so this Euler curve. Euler, all these Euler formula. Questions? The key is we calculate this L over K, and this is this one. We calculate this is critical standard distribution. Questions so far? No question? And then we look at we just talk about this is the columns with central loading. And we have two case scenario based on L over K. One is Euler, one is the Johnson. Now we focus on another one, eccentric loading. So eccentric loading means that so this is a loading P is not at the center of this is the B. In this case, and we will have this P will have two effects. One is a concentrated loading, but also we will have this bending effect from this guy. You guys agree? You guys agree there? Okay. So here, so bending, we just if we apply P here and we just see and we apply P here, but we have a bending. This is a bending moment, and bending moment equals the P multiplied by this is the E plus 1, right? So multiplied by E plus 1. So E is the distance, and substitute into this equation. Are you guys familiar with this one guys? For the beam, the deflection, the derivative of the deflection with respect to the position can be approximated as M over EI. The assumption is this deflection is not too big. Have you write down it? If the assumption is if the deflection is not too big, I can use this one to describe my deflection. With X is the position, So this is the Gaussian equation. We call this a Gaussian equation. I'm just a plug in, right? So using this plug in here, and so you can solve this solving with boundary conditions. The boundary conditions is see, one is x, okay. This is x is vertical. When x equals 0 and y does not change, or y equals 0. So this is one boundary condition. And at x equals L, and x equals L at this point, and so y equals this equation. And y is calculated using this equation. So this is the analytical equation. If you are interested in the derivation of it, come to see me. I'm going to show you. Okay. But I will not test your understanding of this. I'm more interested in the abacus modeling. Even this one, you apply load and you use abacus to get the numerical results. Right? Questions? No question? No question. We'll move on to the next one. So at the middle point of the still for this case scenario. At the middle point, we know the delta is maximum. So this is when x equals half L, and so we can get this delta, the deflection, as M maximum, the corresponding is the bending moment equals P E plus delta. E is a distance between the applied load, the point where you apply load at the center of the beam. One more time. E is the eccentricity. It is the distance between the point at which you apply load and the center of the beam. For this case, it's here. The distance from A to P. Right? So this is E value. The maximum compressive stress induced includes axial and bending. Still this one. So as I said, guys, so this guy has two effects. One is a compressive and one is a bending. Sigma C is a compressive, and we have P over A plus MCI. So that this is the effect of the bending moment that generated by the P. So if we have M substitute M maximum until we into this equation, and from that from 4-48 we can have sigma C, the maximum one, and using SYC as maximum value of sigma C, and solving this for this one, we can have this YC. So SYC is the yield strength of this is the column. And second formula, column formula is a P over A. So this is one. So this is another. This is a concept. Okay? Eccentricity ratio EC over K. So here is a design chart of secant column volume for various eccentricity ratio can be prepared for given material. Material is the strength. So let me ask you guys. I will not test your understanding of this. Okay. We are going to focusing on is the central loading case. For this one, I want to just expand your horizon to knowledge base. Okay, this is the equation. This equation is kind of yes, right? You guys do like this equation? I don't know. SEC part of the denominator. Okay, this is one example, guys. This example is important to solve the problem I'm going to show. So develop specific Euler equation for the sizes of column and having two conditions. One is a round cross sections one is rectangular cross section. Okay, so here, this equation, and PCROA C pi E L over K. So this is equation 4.44. So we want to, this is Euler equation, okay? Divide specific Euler equation for the size of this one. And for round cross section and this rectangular cross section. And how to do that? And we need to take a look at here. For the cross section, and for this round cross section, for the A, for the round, and for the round, and suppose we have the D, okay? So we have the diameter of the D, and then we can calculate this A as I and D power 2 and square 4. I'm sorry. ID square over 4, right? You guys agree? So look at that equation. What do I need? I need A. I need L over K. So K, what is a K as? What's a K? As I said, and K equals square root I over this A, right? You guys agree? So that's from the definition of K. And then I just calculate this K. So what is I? And for the round, I is equals ID power 4 and 64. And I want you to memorize this one. Therefore, for the round one, and J equals 2I, I equals ID power 4, 64. So I is given, A is given, I can calculate this K, where you can put this A and I into this equation, you can calculate this K equals and D over 4. So D over 4. And then you just plug in, so you can have calculated this D equals K is D over 4, K is D over 4, and you just plug in, and you can calculate also, and plug A in that equation also. And you will have, we can calculate this one as 64 and PCR L square I cubic and C multiplied by Young's modulus 1 over 4. What does it say? It says that if you know the case scenario, the ending condition, if you Young's modulus, if you know the length, and then given a load, I can use this equation and to calculate the D, right? So our course is called machine design, right? Right? Machine design means that give me a load, give me Young's modulus, I want to know, give you the structure that satisfy your needs. So I have a load here, length is given, Young's modulus, case scenario, I can use this equation to design a column with appropriate, this is the diameter.
And that diameter, is that like the largest diameter you can have before without buckling, or like what does that diameter mean?
So I'm not talking about the alteration of this diameter. Just suppose this diameter is constant, it will not change. Also here there is another assumption for all this problem is that the diameter of the column or the cross section of the column is constant throughout the structure longitudinally. Right? Questions, guys? No question? No question. So second one for the B. Second one for the B is rectangular. So this is rectangular. And this is rectangular can be this, rectangular and can be this. So how to solve the problem is, so for here, and for I equals B H power 3 divided by 2. Right? You guys agree? The B is a base, H is a height, and this is the base, this is height, this is the base, this is height. And this is A, the cross section H equals B multiplied by H. Right? And then I is given, A is given. Now we still use a K, and K is the square root I over A. And if you plug in, so this is gives us and square root and H squared divided by 12. So this gives us 1 over 12 multiplied by H. So this is our case. So you can just substitute. So this is a K into that equation, right? Into this equation. And also A is into this equation. And you will have the B. So, and these are two cases, guys. The two cases. So let me ask you, for this is a two-case scenario. So which one, in which direction, it will lose the stability first? This way. Right? You guys agree? For this one, if it goes this way, it's much easier instead of this one. So we assume, okay, because the H is lower than B, we use this H, and so this is the B, the base. So this one is easy to be collapsed instead of this. So we have, so you just plug in, we have this B and equals 12 PCR L square and pi square and C E and H cubic. And our assumption is H less than B. H less than B. Does that make sense? Look at my cell phone. I love it very much. My icon, right? So you can this cross-section area. So I have this my for this one. If I compress it, I don't want to break it. If I press it, can somebody tell me how this guy will lose the stability? In which direction? It will go this way, okay? You agree? It will lose the stability this way instead of this way. That is why, because the B is much higher than H. You can see this is I. The height is, if the B is much higher than H, and so this I is much lower than you switch it B and H. You agree? That's the reason whenever we have a rectangular shape, it always loses stability when you bend it this way. Then we only think about this one, or we just think about this one. You guys agree? Don't believe me? Yeah, go home to build something, and you just apply load to see in which direction. So this column with a rectangular shape cross-section area, and we will be losing the stability. Always this way. So this is what I just told you. Now we have one problem is, so this is one example to solve. And this example, we're asked to specify a diameter of the round column, longer that is to carry a maximum load estimated to be 22 kilonewton. So maximum load is 22 kilonewton. Use the design factor. Design factor is a safety factor. Okay. Design factor is a safety factor. ND equals 4 because I'm very conservative. I don't want to damage for this case for this column to damage to hurt anybody. And consider the ends as a pinned is rounded one. Pinned is C equals 1. The column material selected as a minimum yield strength SY 500 megapascal. And modulus of elasticity, Young's modulus equals 207 gigapascal. So how to solve the problem is, so there is a design factor here, the design factor, right? So design factor, and we shall divide a column for critical load. So the P, and P is a maximum. P is a maximum load. The safety factor, I want this safety factor is 4, right? Then why this define? I want to use a critical load that is 4 times of the maximum load. Because as I said, I'm conservative. I don't want to be hurt when this column collapses. I don't want it to hurt anybody else, right? Otherwise, I will be in big trouble. Okay, that's great. So that's the reason I use a design factor or safety factor always greater than 1. Here, and we are very conservative. We use a 4. We use a 4. That means the design, the material, the structure I'm designing is 4 times than the maximum load and this material can carry, or this structure can carry. So this is my PCR. It equals 4 times is 22. I have 88 kilonewton. And also because the 2 ends they are rounded and they are pinned, and C equals 1, right? And then based on this equation we just derived here, because it is a round. I have this equation. PCR L squared pi CE, and I just plug in PCR 88. The L is 1.5 millimeter. You can see I'm using the standard unit. So you need to be consistent, okay? So standard unit. So pi, and this is C equals 1, and this is Young's modulus. I'm using the standard unit. What does that mean? That means length, I use a meter. And but here 207, it is given gigapascal. The gigapascal. Right? This is the length 1.5 meter, and Young's modulus equals 207 gigapascal. So gigapascal means what? I need to change this one to Pascal, right? So Pascal 207 multiplied by 10 power 9 is my Pascal. You guys agree? And then this is 1.5 square. This is PL. This is kilonewton. And so this is PCR equals 88, and kilonewton is not a standard unit, and I need to change this one to 88 multiplied by 10 power 3 Newton. Do you guys agree? So you can see this Pascal meter. Then I can use this one factor and this factor and this factor in that equation. You guys agree? So that's the reason why I have 10 power 9 here, why I have 10 power 3, 1/4 here. So Forget about this. So this will give you a meter, right? This one multiply this term will give you the result of meter. But now meter, when we design a column, if we use a meter, that is for diameter, that is very, very ridiculous, right? Very funny. You can see so big a column, no, right? And that's the reason we change it to the millimeter. We multiply with 10 power 3. That's the reason we have here. Questions regarding where this is a factor is from? Questions? So you need to be very careful. We are mechanical engineers. The numbers matter, also the units matter also. Be very, very careful. You need to use the units consistently. So after you get this D here, okay? And then we calculate this is L over K, so the actual L over K. This is 150, it is ratio, it does not have any unit. So this 1 L over K, that's an actual slenderness ratio. And then we calculate the critical slenderness ratio, and here, using this equation. And so we just plug in. So also keep in mind, you need to unify this is the units. Make sure you use the good units here. So SY 500 megapascal. That's the reason we have 10 power 3, 10 power 6. So Young's modulus 207 giga. That is we have 10 power 9. So this gives us 90.4. And then we compare this ratio, critical ratio, and with this actual ratio. That means the actual ratio is greater than this is a critical ratio. Okay. We can use Euler column. So we use Euler. This is a formula. So we can select and t equals 40. If t equals 40 is close to this one. Any questions regarding this example? So make sure you understand that this one very, very well. A very similar problem will be given in our exam 1. Sorry. But I will change some values, change maybe some case scenarios, and to test your understanding of this problem. This is very, very important. Okay, I'm going to